Hello, hello, and good morning, everybody. Welcome. Josh Pines is in the audience. Do you mind just say hi, Josh, if you're there? Because I am dealing with a subject that I know it's very close to your heart as well. So I would love you to be able to chip in. Let me see.
I'm incognito. I'm just hiding in the background, and I will let you walk straight ahead and off the cliff, known as film grain emulation.
Okay, very good, very good. So Josh, I have like a kind of prepared a little presentation, but before I go into practical part, I wanted to, but like maybe just, I want to discuss things that I shared with you. And I think everybody in the audience is certainly going to appreciate it very much. I don't think we can find anyone better suited to do this. And this is also very important for me that someone's checking, that what I'm telling you, it's not an absolute nonsense as well. Okay, so guys, let's start. We'll have a little more.
Dado, occasionally it is absolute nonsense, but you do it so well that I figure I just let it ride.
Good, good. Science can be there's a thin line, right? There's a thin line. Okay, now let's go. I want to start with film grain today. Okay, and I have prepared. I'm gonna kill you with slides first. So just so you know, it's gonna be a, death but slides. But I hope you guys are gonna like it, and it's gonna be worthwhile. All right, so let's start. So basically, I want to start a little bit just by helping you understand the the physical nature of film grains, so we can just understand that part first before we move on to like the emulation part. So this is probably the kind of the highest it's like a resolution or microscopic image of film that I found. It's basically, think about this measurement at the bottom shows it that what's 5 micrometers. So it is really like what happens, how film really looks like. So silver halide crystals are basically the photoactive material inside the film emulsion. And, when they get developed, first they get exposed to the light, then they react to the light. And then they group and they form like a little kind of, clouds, and then they are then removed. The silver itself is kind of removed from the dye itself, from the emulsion, and then what's left is just basically this kind of particles. Covered it in the past. I don't want to go too deep into this, but I just wanted us to kind of start with it, understanding to where this really comes from. So how big are these particles is really interesting. They vary in size between 200 and 2000 nanometers. And this is really invisible to the naked eye. Okay, I think it's important at this moment just to notice that this size is significantly smaller than the size of a photosite of a digital camera or a film scanner. And so I think this is an important, because as we go into a little bit later and we start doing more like a emulation, you'll understand the limitations of some of the emulation processes that we are doing. Also, what's important to kind of clarify at this moment straight away at the beginning is that basically the film grain is not actually an effect of a particle, but it's an optical effect. So basically, it's a noise pattern from the density changes of those little clouds on particles, right? So think about it. The density changes means that they vary microscopically in their kind of exposure level or something like that. Think of it like, so maybe that's a kind of best way how to describe it, right? So it's an optical effect, really. It's not like a necessary a particle effect that we always think like, oh, we just put noise in and so on. It's not really what happens. Okay, so diving a little bit deeper into what really happens on film is basically the latent image first gets formed when it gets exposed to the light. The reason why we call it a latent image is because it's not visible to an eye that anything has changed on that image. If you look at the exposed negative, you don't see any difference, but actually inside the emulsion, the silver atoms have reacted and they have bounded, but it is not necessarily visible on the surface of film negative at the moment. And then we do the chemical processing, and then these developing agents then basically, help, that dye, that is inside the emulsion in connect with the silver halide crystals or activate them. And then that's basically when they become visible. That's basically when we really start seeing, those clouds, right? And now you have to understand this. The way how film stock is designed is that it has. We'll see now. Like as soon as I'll show you, but basically the size or the amount of silver halide crystals is directly correlating to the speed of film stock. Okay, so think about it. If silver halide is an active material, that means that the more of silver halide there is in film, the more photoactive it's going to be, the more light sensitive it's going to be. That means also the grainier it's going to appear, obviously, right? But also you have to understand that inside the normal kind of, film emulsion, there are sublayers, and these sublayers are made from different sizes of silver halide so that they can respond to different levels of light, okay, light exposure. So basically in general, you have to understand that the size of these crystals is directly related to the sensitivity to the light. So clearly, the bigger the size of bounded crystal means, that they were sensitive to lower light, and the smaller they are, that means that they are sensitive to higher light, because, think about it, more light, you need less photoactive material. And these sizes are measured and this is post-processing. Once we have processed the film, so this is not the actual material that we have put into the film negative. This is after we did the photochemical processing, and there is actually a method of measurement that is really well established. We'll learn about it as well, and that method is measuring film grain size between 0.5 and 2 micrometers and 0.1 and 0.3 for the fine grain stocks. This is just still, again, I want to just make sure they understand this is still far smaller than what a digital photosite is. Okay? Now, why I'm wanting you to understand how we measure this grain, because when, let's say we are now in the process of film grain emulation, we have to find some quantitative method of understanding whether we're doing our job correctly or not. Right? So, or we need to kind of find some way how we're going to have some numbers that are going to help us understand to what's happening. We need a method of measurement. And lucky for us, we didn't have to invent any of that. Kodak has done a great job, and they have something which is called Kodak grain ruler. Okay, so it's kind of the standard method of measurement. I can share with you a white paper from that as well, or kind of, it's rather less of a white paper. It's more kind of instruction document to how to use this piece of equipment or this method of measurement. You need a very, very expensive equipment for this. I don't think it's not like for like anybody outside laboratories to do that. And there is a lot of complications we'll see, especially later with negative and print and so on. But there is a method of really what happens, and we measure an area of a film, and that area gets heavily amplified, and then based on that, then we basically then decide to create a number or assign a number to the graininess of that image. Okay, so basically there is kind of an index number that tells us, oh, how grainy is this image. So like, you could say, oh, this film stock is grainier than this film stock, right? So there is a number that kind of describes the graininess. Now, the method of measurement, it's called the RMS granularity method, and the RMS stands for root mean square, basically, which is a mathematical term used to express a deviation from the mean value. So like it's a little statistical in that way, but it's a very, very common method in physics that we use for physical measurements and measurements of any type of deviation from normal. Now, this is important for us now, since we are like getting super professional with understanding film grain. We're not just amateurs anymore. You guys are now becoming really well trained in this. And I want you to be able to kind of like differentiate between two terms that are very important that we are going to be using. And when we use these terms, we will be referring to exactly a particular thing. One thing is called granularity. So that's basically granularity is the physical measurement. So let's say when I take this device and I measure, how much grain there is, it's called granularity, okay? And then we have a graininess, okay? And that's the subjective perception, okay? That index number that we are talking about is referring to the graininess. We're trying to give basically a perceived value to the viewer. Okay, that's really what we are trying to indicate. The granularity itself, the numbers, there is many factors that can take a granularity to a different level of graininess. For example, exposure levels, or for example, scaling an image. So image with low granularity when scaled is going to have a higher graininess, for example. So, right, so there are two different terms. You have to understand you could have a very, very fine grain on let's say film negative, but you could end up with a very high graininess depending to what you do to it. Okay, so these are two separate terms, and we just need to really, really understand this. So the grainness is really what that level of variation of the density that we see in an image. Kind of that would be the kind of the scientific kind of description to what it is. So now that we understand that we are able to measure, we're able to quantify, then we study what happens with grain. And in those studies, and by the way, these studies have been going since, decades, okay? What I'm showing to you here is there are some things that are new. At the end, we'll see. Actually, there is one research that's brand new that I haven't necessarily even there to share with you that could be a completely separate talk. But think about it. This is nothing new. This is I'm really drawing from decades of research here. So nothing here is questionable that I'm going to give you now, except if Josh kind of thinks that I'm saying a lot of nonsense later on. We'll find out. But what I'm going to give you is facts that are really about film behaves right now. So let me tell you that number one fact, which is really apparent, and it doesn't take a genius to understand this, is that the grain or graininess is exposure dependent. Okay, it makes sense, isn't it? The lower the exposure, the lower the film is, then of course it's going to show a more stronger pattern, a larger silver halide crystals. So it's going to be more prominent, more visible to us, or it's going to feel like that. And then improperly exposed in the mid-tone, it has optimal grain structure. When you kind of, look at the mid, when you say, oh, the exposed is very nice, my God, image just feels so clean, which is why a lot of tests, film looks so clean. Why? Because they don't really, they've been properly exposed so that we don't really see this problem. Now, interestingly, in general, higher exposed images show much less grain, but in some stocks, that grain gets denser. Okay, even though it's less, it becomes denser. It becomes more visible. Okay, so this is the difference between granularity and graininess, right? So basically, but in general, we can say that there is a strong correlation between grain and signal, right? So the lower the signal, the grainier image is going to be, the higher the signal, the finer the grain is going to be, and less noticeable. Okay, so as we can see, this is in this slide. It kind of says yes, on low exposure, I need more silver halide to get together to be able to depict this image, to capture this light. So it's going to be larger, pattern. On high exposure, I need it very small. I included here this chart because basically, what we really, for us to really to understand, where we are doing what we're talking about here is basically, this kind of, toe of a film, where we start seeing a quite significant amount of grain, right? And then this shoulder as well, where sometimes we see higher density of grain, even though the grain's finer, it becomes a little more dense, right? But this particular curve here, which by the way, in film terminology is called gamma, is effectively a ideal kind of curve where the grain behaves as we want it. And keep that in mind. Mid-gray is that ideal curve. Okay, just keep that in mind. Just keep it in mind. You'll see why that's going to become important very shortly. Okay, so to kind of just underline, understand one more time. When the image is slightly underexposed, the grain is coarser, right? In shadow as well. In the midtone, it looks like an ideal size. It's optimal. It's evenly distributed. And when it's a little higher, it's fine grain, but it's getting a little denser. And a maximum, the grain is very dense, but it's very, very little visible because it just it works like that. Okay, now that we understand that principle, then it makes absolutely complete sense that when we bring the actual film light sensitivity into that game, that this is also going to correlate, isn't it? Because if we say, okay, I have a film stock, basically, which the light sensitivity in film is measured in ISOs. And when we say like okay, the higher the ISO, the more light sensitive it is. So what does it mean? Automatically means, oh, I need more silver halide crystals in it. And if I have more silver halide crystals, it means I'm going to have more grain, right? So higher ISO films and lower ISO films have significantly different characteristic when it comes to the perceptual graininess. And that's basically the fact, So, and how they say, like, again, keep that in mind that, sometimes, we are like really trying. Now, don't think about it like, this is a starting point. So if I have a high ISO image that's ideally exposed and it's already grainy, now think about what happens with that high ISO image when it's underexposed. Then it's very, very grainy, right? So, so the ISO is just a starting point. It's just a kind of baseline to what we can expect from that film behavior. Inside that baseline, there is a still variation between low exposed parts and high exposed parts. I just want that, to register that, So this is kind of just a, what is my material? What I'm dealing with? What is my baseline? What is my mid-gray? How is it behaving? Another thing that we also noticed as we were working with film, and now you will see why I'm pointing out to all of these things because you're really going to need them. And this is one of the things that has been ignored. And I think I can't believe actually that, very rarely I hear people talk about this fact, which is that basically that grain has got the color content, right? We never think about it, isn't it? We never think like, oh, grain is we think always a grain monochromatic, and we understand why, but it's actually not, because if this is a kind of a modern kind of negative film emulsion, and as you can see, it has multiple layers. In general, what we can see is that ignore now the protective layers and just focus on these layers that have a light sensitive matter, and then you'll see on each like a light sensitive layer, like for example, this is a blue sensitive layer, that captures yellow color. We can see that there are two types of emulsion in there. One's that's sensitive to high exposure and one to low exposure. For example, for the in magenta layers that are responsible for green color, we have even 3 different kind of exposure level kind of sub layers, right? These layers are responsible for different exposures. So, and then when we come to red, especially for red, that are responsible for cyan, and we'll see this is a blue color. It's probably one that's always noisiest, right? Because of the light frequency, we also have 3 of them, right? So think about it. Each one of these layers is producing a film grain that is in that color, right? It's not black and white, which is what we always see from all these kind of plugins around, right? So and within that color, there are multiple effectively types of silver halide crystals that have different sizes as well. Okay, so just think about it. This is really, really an important, also like for you, what you should also always, kind of, have at the back of your mind whenever you're trying to emulate film is that blue is always going to be the highest, right? Because it's just also, it's kind of generally to do with the light frequency as well, basically. And there are several other elements like chemical sensitization, dye cloud formation and so on. Yeah, go ahead.
The main reason why blue is always the grainiest?
No.
It's the same reason why it's also the noisiest in digital cameras, because our eyes see virtually no detail in blue. It was a engineering decision to put the grainiest, noisiest signal in the color that we do not perceive detail.
I see. Because then we see the least amount of the other noise. Interesting. Interesting. I love it. Okay. That's another fact you see. Thank you. I need to add this to my slides. Thank you, Josh. Keep it coming. Just keep it coming. All right. So let's go. So basically we have a blue channel, highest grain level, and we just learn because we see at least amount, so we actually notice it has highest amount of grain. Green is moderate grain, right? And red is the lowest amount of grain. Okay, really important fact for all of you now to understand this. Okay, so think about it. This is really what film grain really looks like, and 99% of the times when we talk about film emulation, we never even consider that color factor. We never even talk about this color factor. Okay? And then comes the next kind of observation, which is super important for us. It's a big part of what we do as emulation, and again is so ignored. It's so not even like I look at every single film emulation tool out there, almost every single, right? And you'll notice that this is a really another fact that has been completely skipped, and that there is a huge difference between negative film grain and print film grain. They are two completely different things. Okay, and negative grain is basically the original capture grain, and that's the grain that we've been pretty much kind of talking about. It's kind of very much signal dependent. Okay, but it's very consistent, by the way, as well. It's very, very consistent, and it's very fine, by the way, as well. Okay, but print grain, on the other side, has got the compounding effect of the negative grain characteristic and the print grain, which has its own grain. Okay, this is kind of, again, one of those things that that we completely ignore, because when we print, we don't just have a grain in print. No, we are taking that, we're inheriting the grain from the negative, and we are printing it. We are transferring it onto another medium that has its own grain, and it happens that that grain of print medium is actually stronger. Okay, in some cases, there is also process of optical enlargement that's involved in it. Like sometimes we used to shoot on 16 mil and blow it up to 35, which used to make image very grainy. But also think about it. Once we have transferred the film, to print, that print needs to be enlarged, needs to be projected. That amplifies the grain significantly, or needs to be scanned into whatever resolution and showed on like a large screen, which again amplifies the perception of the grain. Okay, so these are very, very important factors. So there is like a real situation that print has got a grain on grain situation. And that's a very, very important element that is very often completely ignored in film emulation process. So just to kind of recap, the negative grain, the characteristic of it are relatively easy to predict because they are a direct result of exposure. They are signal dependent, right? They are dependent from the original signal structure, because what that means, like what's the ISO, and they are channel independent as well, because you have, as we learned, different channels that behave differently at the amount of grain, right? So, and distribution is really related to the exposure, to the density. Okay, this is, and it has a color, very important, right? And if you now take that negative, and you scan it, that really appearance of that grain of film negative is hugely going to depend on your scanner. Like we had like a master class in scanning. I think I should do the one class like that where we basically compare different film scanners and different results, and the appearance of grain from different film scanners is enormous. It's so big because of the resolution of the scanner, the technology behind the scanner, and so on and so on. So it's like you have to understand there is a lot of variables there. But on the other side, when we come to printing, it gets even much more complicated because now we're combining two grain together, right? It can be that negative grain somehow got a little enlarged because it does go through an optic, but the contact printers usually don't have a very strong optics, right? And basically, and it's also a nonlinear compounding effect. Okay, what does it mean? We'll see the math in a minute. Basically, that it means that this is not like a plus. You don't go and say you add one to another. Actually, they compound in a slightly nonlinear structure. So what does this gives us ultimately as a result? What you wonder why this matter to me? Because it gives you a larger appearance, like and basically, it has a very complex spatial frequency mix. What does it mean? And we'll see that means that there is, because we're combining different grains and different sizes, the spatial reactions is very good. This is probably maybe a good segue to maybe this is something that I could cover in my next, love stream, which is dealing with spatial frequencies. This is a huge subject, that for film emulation, again, that hasn't necessarily been explored so much, but I think maybe this is something that we could cover next time. Okay? This one is just because I know that you guys love the math so much, so I couldn't really resist not to share with you the formula for this. So please, everybody, screenshot this. This is super important slide. You want to see the mathematical relationship between the negative grain, print grain, and the granularity, right? And why this is a nonlinear relationship. As you can see, it's all, on square function. So yes, usually kind of light and film behaves in such a way. So don't be surprised to see that. But basically what we can see is that that grain actually moves exponentially. Okay, this is just really important proof, mathematical proof as well. This is not just, a theoretical. So uh, again, a really important kind of factor that has been ignored in digital kind of in emulation for so long. So basically, kind of just to give you like a little overview. So the negative, let's say for example, like Vision 3 has a grain size of around 8 microns. And when we measure its granularity, this is based on Kodak's charts. We're at a number of 4 to 5. So this is the Kodak measurement. So we are at 4 to 5. This is very low, by the way, right? And we start seeing that grain directly on a negative when we enlarge it to 10 to 20 times. Now, think about it. If your image is 24 millimeters by 18 millimeters, it's not very actually, easy to see it itself. But once you scan it and enlarge it, it becomes visible. But, you need to enlarge it significantly to start seeing it. Now, think about this now. So the optical printing, the print, which is a one-to-one, it's usually one-to-one. Let's assume it's one-to-one because we haven't been doing a lot of 16 to 35. The print stock actually has got the very relatively small grain of just around 3 microns. But because of that compounding effect, we end up with the final print that ends with a granularity of 6 to 8. So see, even though we have a material, which you say film prints got a very fine kind of granularity, but somehow it becomes at the size of 8 to 16 microns, right? But the granularity, RMS measured granularity number is 6 to 8. And that's let it settle in, you see because you could just say, oh, give me just a print grain separately. It would look one way, negative grain separately would look one way, but let's combine them and we end up with a completely different result. Okay? Just kind of, it's just very important thing to understand. What you were always seeing, every film that was shot on film and distributed on film, you were always seeing final print. You never saw one another. It was only later when we started distributing on digital that we were able to see non-film print grain film, right? But this is really reality. When you say, oh, I like film grain, well, you are really talking about the final print, not the print itself or negative. You're talking about the combination between the two, okay, that have got together in a very nonlinear way. Okay, so for us, the main takeaway is never treat them as the same when building film emulation. Okay, we're going to see also a little bit about that. Okay, all right. So I'll maybe like skip about this scanning, because right now I'll talk to you a little bit more about it. It will make much more sense once I explain why I'm making all this, analysis, why this is really important, because I really think it's an important moment in the history of film emulation for us to debunk the mid-gray scan method. Okay? This is absolutely flawed methodology, yet it's most widely adopted way of film emulation. 9 out of 10, film emulation processes out there do nothing else but basically following, right? What happens is this: we expose or we shoot, a gray card, mid-gray card, and then we, scan that piece of film with a usually only negative, usually only print, right? And then we kind of layer that kind of piece of film scan on top of an image with an overlay mathematical method, and then we kind of end up with a grainy image. Okay, and it's look, yes, I've used it for years just because it was a fix. It was no other way how to do it. If I wish we had the knowledge and technology how to do it back then, I would have used it. And I really like, actually, I have to tell you honestly, there is actually plugins out there that claim to be thousands of dollars and stuff like this, that are doing nothing else than this, right? So they make it a little bit more sophisticated, but they all have that significant problem, is that they start with a film scan. And let's kind of now understand why this is a flawed problem, why this is not the right way how to do it. Okay, so number one, we just learned that the real grain varies with luminance, but what we have here is only one luminance level. And it's actually the ideal level. Yeah, mid-gray is perfectly in exposed film. So you only see one type of grain. There is no variation between highlight and shadow. You don't really see that. Okay? So it's only one exposure level. You need to really see what happens in shadows and in highlight. You need to see all those levels to really be able to say, this is what film grain, behave. So it's really violating the fundamental physics of what's happening with the grain. It's giving you just a very narrow view of what grain might look like. Okay? So it's wrong. It's wrong to just sample mid-gray, because you are going to end up with the same grain no matter how your source image is exposed. Because you take that grain with the same texture, you put it on your image, and your image could be underexposed and overexposed, but yet that grain texture that's going to be sitting on top of it, it's always going to be the same. It's not going to change based on the exposure. Okay? What is correct? It's correct that on a low level, you would need to see different grain, which is probably going to be bigger in size. It is bigger in size. And in highlight, you need to see finer grain with higher density. That higher density is also very important because it's part of that highlights roll-up. There is another major issue with this, okay? Again, maybe this is another thing why I'm really excited, that I started this series, because, I personally have spent a lot of time researching the whole concept of spatial frequency. This is something we didn't even realize it's there a lot, at least talking from my own kind of, angle. And then once we have started using AI image analysis, we stumbled across this kind of incredible amount of information that's inside film scans that is living in that kind of spatial frequency domain. Okay? So what happens when you scan a piece of film, you end up with a fixed frequency content regardless of image density. Why is that? Well, this is just the reality that you have a fixed grid, right, of photosites of exactly the same size that, based on the Nyquist theory, are all going to sample exactly the same spatial frequency. Okay? But the real grain has got completely different frequencies. And now, if you think about it, if we try to bring that negative print emulation, you end up with this super complicated and super sophisticated spatial frequency results that film scanners can't really resolve because they are not built for that. They have a fixed frequency, right? So there is absolutely no relation between that kind of fine, much smaller than photosite, response of film and actually what you have scanned. Okay, so you have a real problem. Then there is another major issue with this, which is a huge problem. There is no color. Why? Well, we scanned against gray. So what happens when you expose image against gray? You end up with gray. We end up with no color, which is why all the film emulations out there are black and white, are basically just monochromatic. Yeah, because they never sampled against color. They never actually analyzed an emulsion that has color information embedded in it. We've been analyzing film emulation with no color in it. And we were just getting away with it because on a luminance channel, it kind of felt like that it blended with the original color of an image, but actually it's not, right? Real film has got a very, very specific interchannel coloration, very specific. We've seen, what happens with blue, green, and red channel, right? And this is huge part of that, whether your grain has blended with an image when you emulate it or just feels like sits on top of it, and we are really, why we are actually trying to do all of this is because we want grain to be part of an image, not to break the illusion for the viewer that there is just a layer that they're looking through, right? Okay, there is another issue, which is basically that this method of work that we're using right now of scanning film is very much resolution dependent. That means that if you scan film at certain resolution, well, that's the only resolution you're going to be able to use it, because the moment you enlarge that scan, you basically start getting very pixelated and unrealistic results. So tough luck if you scan your grain at HD, or what's happening, for example, with some of these plugins is they emulate at, let's say, HD resolution, right? And then you kind of put it on a 4K image. What they do is they scale the scans that they made in HD to 4K. And that's kind of, blows it completely. I'm not here to kind of, write anybody off. I'm just basically telling you that this is a real problem, right? Okay. In reality, the grain must be resolution independent. Okay. It cannot depend whether you're working in HD 4K or 8K. You always need to be able to get an accurate grain representation. Okay? So this is a really, really important factor. So what's the solution, you ask yourself? And solution is always scientific, right? We need to deploy science for these things and find the answers to all of these problems through the scientific studies. Basically, there has been a whole evolution of research-based approaches to film emulation. And I'm going to introduce you to 3 major papers. I was going to bring a 4th one in, but, I haven't necessarily been able to show you exactly all of the examples. But right now, I want you to get familiar with these 3 methods. Now, look, most of the stuff that I'm going to show now in this part of the presentation is available to a very small group of a research community. I really hope you're going to appreciate that I'm opening the doors to you. It might sound a little dry, but I think you should try to memorize and understand these things, because it's really going to help you understand what really, works and what drives this development. Okay. So back in 2007, we had a first paper. We'll learn about this paper as well, that has opened us to an idea that grain should be, generated, right, instead of scanned. So that was the first breakthrough where we said, like, okay, instead of just, using this approach of film scanning and using these scans, right, we need to kind of, find a way how we're going to be able to generate a grain. And the first attempt was in 2007, where we started, working with the spectral foundation and analysis of an image and so on. So we'll go deeper into that. We already started doing some practical implementations, maybe at least from what I remember, I was at SIGGRAPH that year in 2006, and that was some first, practical implementation that I saw. That later found their way into a software called Nuke from Foundry. And then it was probably not until 2017, until the last really interesting paper I saw was in 2023, that we have actually created a huge amount of new research and new developments in the physical reality of film, and being able to, utilize Boolean models, true resolution independence, and then we also seen some real-time performance, even though that real-time performance is still very, very low, but we've seen it, we started seeing these things. So really, it was, let's say, 2017 to 23 that we saw a huge amount of, improvement in that respect. So this is the first paper that is significant, and I think it really needs to be mentioned. At least, I draw a lot of inspiration from this paper. It's called Stevenson-Saunders spectral approach. So that it's using a core concept that is basically creating it's doing so-called noise power spectrum. Okay. So basically, the first thing that this paper did is showed us, hey, we can work resolution independent. Then basically, I think that was really the main breakthrough, right? We finally started seeing a grain that was, generated on the actual image resolution level, and it wasn't like a kind of implying a scaling existing thing. And basically, it was primarily used to regrain images that were, CGI, your computer generated images that we needed to blend back with the film plates, and it was really designed and built from that perspective. But it had a lot of flaws. I mean, it was a significant improvement, but had some problems. So basically, I had zero phase information. It wasn't able to form individual grains because it was really like a signal to noise kind of, based. Even the author said individual grains do not vary in density, but rather the number of developed grains change, right? So basically, it wasn't really adapting to an original image at all. It was still felt like it was layered on top, but it was giving us, for the first time, complete resolution independence, and showed us that there is actually possibility for us to generate grain, to make a grain, in an algorithmic approach. This paper came a few years later by Stefano Collis and White, and it's called Adaptive Synthesis. It's really, what found its way, later in Foundry as well, and what the kind of, Steve Yadlin's idea is around it, and it's absolutely no rocket science. A lot of people have adapted to it. It's definitely like a one that has ruled, the, generative grain. Basically, what it was doing is it would analyze a grain from a flat area. By the way, guys, this is very interesting for you to know. This method is also very good for denoising, and you have actually some parts of this method in that amazing denoising plugin called Neat Video. Yeah, but that's where the idea comes from. So you sample, basically, kind of, or where Neat Video gets the idea from, right? So this is the paper. So basically, you sample an area of an image, right? Then you design a whitening filter for that specific grain, right? And then you design a reconstruction filter for that. And then you basically expand it, to not to have the same, because you sample kind of in the same area. So you need to kind of, vary that particular area. And then, you apply also correct print density to it. So you finally start getting the print density filter. Why was this really important? Well, it was a first practical information where the grain was physically accurate, that it was change of the density. It recognizes that grain statistics are not really Gaussian, it works on a different level. And it was very good because it was able to provide addition and removal. Neat video is removal, but you could actually, like, probably, I'm not sure, but one would be able to hack like something like neat video to be able to regrain images, based on that. And this is the foundation, really. This is the kind of what you currently find. I think it's called regrain or dust grain or something like that. The tool in Nuke that is kind of de facto standard in compositing industry for regraining or matching the textures from one image to another. And yes, this was also the method that was deployed in the first version of GrainLab. This was really like the method that shined through, but had a certain, like also, like a certain, it removed certain, limitations, right? Basically, it was responding to an image itself, right? So it wasn't just a random layer put on top. No, actually, it was additive to the image itself. And also it added that much missing spatial structure element that we were missing. The frequency were responding and much better. And a lot of people were responding extremely positively, like I remember when we released the GrainLab very first version, people really, really loved it, because it just, had that frequency level in it. Okay. This is the paper that, to my mind, it's kind of the de facto paper right now. Like this is what you guys also have in GrainLab version 3. Now I'm spilling my beans. I'm telling you where the science comes from. But, I suppose, that I want you to benefit and to understand, what happened and why the new, method is significantly improved. Okay, so basically what happened now is that we have now a completely new Boolean method of physical reality. So it models actual silver halide grains as actual physical particles. You understand? So it's not like it's not using noise. No, it's actually modeling the grain, which is why I kind of called it secretly a B grain, right? Because a silver halide is not two-dimensional flat. It has its shape, right? It's a three-dimensional shape. And it is also incredibly exposure dependent, which is super important part of that kind of problem we had with film scans, that they would, look completely different in shadow and completely different in highlight. Okay. Also, it has an incredibly good physical accuracy. That means the grain size is you are still using the real film. Like basically we need a film source. That's the starting point, but we are not starting just with the mid-gray. I can maybe in the future share with you those test images that we have used to sample the textures that are used in GrainLab, for example. So we are using actual, film that's underexposed, overexposed. So we are using the real film results, right? It behaves on that kind of, spatially accurate frequency level. And basically what's also super important is that it is totally density dependent. So what happens is with the different exposures, the particles don't just get smaller, they also are getting more dense. And that was a huge thing. That effect is super important for the highlight control. And then when you combine that with the JPlog2, you get an incredible good results. That's basically really where we're at, right? And what's really important is this as well, is again, this is a completely new method. It's not layered on top. It doesn't live on top of it. It actually absorbs the light. So it's using the process of multiplication, and it's not an additive process, right? So it's not like something you put on top. It's super, super important, right? It's using Monte Carlo simulation, which means that because of that, it's in frequency dependent. This is something that comes from CGI, but it's a model of rendering that is totally resolution dependent. If you zoom in into it really, really high, you'll be able to see singular grain texture, which was not possible in the past. However, it's super computationally intensive. And that's why when you don't have like a beefy machine and you switch GrainLab into K, you start stuttering. It's basically this. To my knowledge, I said there is another paper that just came out, in 23, hasn't necessarily caught up a lot with everybody else. It's using GAN, for creation, but because of its kind of, reduced resolution, we need to find workarounds how to do it. It has a great results, but in a very small patches. This one is definitely deployable even on 8K, what we're talking about, but this is definitely what I would say is currently the state of the art. It models actual physics. It grain forms the image, right? So it responds to, content of an image, right? It's completely resolution free by the design. Right now in our implementation, you can go only up to 4K. If you go more than that, it's actually scales itself, and it matches film. Like if you like let's say zoom in, right? And you will notice that it behaves exactly because of that, and also gives us a lot of parametric kind of control as well, which is important because we don't want to just kind of have a same grain. We want to be able to design and shape grain to look like we need it, for certain elements. Okay, so why are these methods is superior to just use scanning a film? Because they vary on signal. So that means that that problem that we explained at the beginning, that the higher exposed look one way and lower exposed look another way. These methods that I just showed you here are able to emulate that part. They are modeling the actual physics of grain, especially the last method, and they're they're completely resolution dependent. It doesn't mean that you kind of like can scale it to any resolution because there is a computational limitation, but these film grains look correct in HD or 2K or 4K. Basically, they look exactly the same. They are scaling with that resolution, so you're not scaling the actual texture. Now you probably go and ask yourself, "Oh my God, Dado, you're just why are we bothering? Why are we going through all of this? Like a kind of thing." So I wanted to include just this. The grain to me should add to the visual quality. It shouldn't take away from it. It should be something that is improving your image, right? Not degrading. So a good quality film emulation is going to do exactly that, right? It's going to look natural. It's going to look organic. It's going to pass. You can deliver your shows to any, major studio, and sometimes they can fail, based on a signal to noise ratio, or they can find when there is a repetitiveness in it. There's lots of like technical issues that you could do this, by doing a high-end emulation. You're never going to have that. It really, for those cinematographers who are looking for accuracy, it matches the prints and so on. So yeah, it really helps you model more film stocks. It works very well with the film compression, with the transmission compression. Again, because of that increased spatial frequency, we'll see that. And yeah, I suppose it's just overall, matches the film science, and it works, in just much better way. So yeah, so that would be like kind of my slides, kill you by slides. How many minutes did I have? Oh my God, 1 hour. I didn't think, well, okay, I suppose you have to spend 1 hour to talk about this. So before I don't know whether maybe I should leave the practical part to the next time, because we definitely need a good hour just to go and learn how to do the practical part. So maybe I'll just open now to some questions and answers. Maybe that would be more useful to you guys and me just quickly rushing through the, explanations, or showing you practically how to do it. I think it's better if I do a practical implementation of these emulation techniques in my next slide, where we're just going to continue. But I want to now open to you. Please let me know any questions. Just type in X. But before I started, can I please go over to Josh? Josh, please tell me how much nonsense did I share with people this time around?
No, that was very good. My notes are there's a few nitpicks, but I don't want to you know no, it was very good. But if you really want, oh, a little nitpicking on the maths about you're saying there's a power law, but that was for variance, and variance is a square. And if you notice, the actual bottom part of the formula had a square root of the square for the RMS.
Here, what?
Do you know why print film grain is so much finer than camera negative film grain?
No, tell me.
Because when they're making the print from the negative, they have a ton of light. So they can make the print stock extremely fine grain, like an ASA of 2 or an IC, right? Because they can just pump a ton of light through it. Whereas on set, we're very limited. For synthetic grain, well, there were entities putting synthetic dinosaurs in movies and adding film grain back in the 90s. So
what did you do? How did you do it back then?
No. I mean, look, not as sophisticated as these papers, but I do want to say that there was early seminal work done back in the 90s on this, though unpublished because we weren't allowed to
Because you're working for the facility, right? It was not. Yeah.
It was certainly not as sophisticated as these later papers, but there was earlier work that did that. But these papers are great. And yeah, the only last footnote is it would be very interesting to do some tests because a lot of the current deliverables to streaming entities, when those get watched at home, a lot of those, because of the compression issues, sometimes that does destroy some of the film print emulations that are out there. So it would be really.
How do we do this? Should we really maybe go to Netflix and ask them to re-encode some of the masters and different levels?
The footnote here is Netflix is coming out with something which is we analyze the noise and grain, characterize it, give it a fingerprint, and then there will be some way of distributing it and having it added back in at the destination. Sort of like imagine, sort of like Dolby Vision, we send out an HDR stream with enough metadata so that your display device can show it correctly. But I don't think, this is being proposed. It's a good idea. There have been other ideas about this in the past, but it is one of those questions about I put all this work into making this fabulous, texture, and then it gets destroyed when the streaming services compress it for distribution. Anyway, that's all I got to say. I think that was very good. I'm going to go on mute, answer these other folks' questions.
Thank you. I actually think this is you raised a couple of interesting points there. Basically, number one, what I think you said was the fact that that problem with the compression. There is actually, Fraunhofer approach, that I've been, following a little bit. And then also Christian just mentioned Cassiano mentioned in the chat about the wavelet iris approach, which is another kind of research. And there is even a SEMTI paper that kind of, allows you to specify in your metadata how much noise you want to reapply post compression. I think it would be really what our early tests showed, just using our own compressors, not using the same compression that Netflix is using, but using the same type of compressors, right? We found that increased spatial frequencies are great in tricking compression algorithms to not remove some of the detail. So, you can't just do this using only grain. You need to add some spatial information in there, and that's actually kind of thing that helps you preserve some of this amazing texture, as you say, that is in sides. But I think to make this claim really stand, I think we would need to really work with someone at Netflix to help us do this, and I might just as well reach out and see whether this is possible. But thank you, Josh. I really love your contribution, and thank you for being part of this. This is wonderful. Tal, yes, and I'll do the practical part next time. I'll do next Friday. I will be only doing practically emulating grain, showing you how to use it. Jason, you had a question. Please go ahead.
Hi, guys. I certainly wasn't the first with a question, but I think you're going to answer it when you do the practical demonstration. But really, it was when you are applying grain in your film print emulation, is it best to do it post or prior to the look? And finally understand why you have Print Lab as a separate.
Yes, yes. Now the question is not yes or no, right? It's very, very dependent on your workflow, on your desired result, and on your source. And it's so it really depends if you have very clean source or you have a source that already has some texture you're trying to preserve and so on. So when I do the practical, because it's not really you should do it this or this way. You can do it one way or another way, and you're gonna get different results. And it really depends to these elements for you to decide. But you can make a very, very kind of detailed decision to what's the best way how to do it. Like it's not a random choice. You can make you can base on the factors and your desires, you can totally decide where and how should I put this grain. So absolutely. So just so guys, for your information, the new version of FilmLab is going to have two separate grains. So, maybe I'm saying too much now, but now I spilled the beans already, so I might as well. So we'll have a neg lab, which will produce neg grain, and we'll have a print lab, which is producing a print grain. And in between, you're going to have your grading. And maybe that kind of answers your question, Jason, as well. But what we think it's an optimal way. But again, it's not one solution for everything. But yeah, thank you for a great question. Then I have Cassiano said, Dado, I want to know about. Yes, this is what we did. Cassiano, it's a really interesting subject. I'm definitely going to cover it in one of the future talks. I think it's absolutely fascinating. So yeah, we're going to talk about it. Yeah, thank you, Christian, Mario, Dado. Will you put this on YouTube? Absolutely, everything's going on YouTube. Guy, you had a question. Please go ahead.
So my question is regarding how to approach grain. So like much of the stuff that I work on it's small indie films that ultimately are going to be seen on a streaming service, but they all have a limited theatrical release, like film festivals, that sort of thing. And I'm just wondering, like, because obviously the way the grain will appear on a small screen as opposed to how it will appear on a 40-foot screen is vastly different. And I just wonder what's like the normal approach for that. Are there typically two masters prepared? Okay.
Yes, that's exactly what you want to do in an ideal scenario, right? When when the budget and time allows, you are really anything that's going to go theatrically, you want to sign off on a big screen, and you want to, at that moment when you're signing off, you want to have that kind of dial available to you to go and fine tune your grain amount or characteristic while you're doing it, right? You will see, like, your grain's going to look amazing on your LG, but the moment you go to a cinema, you put it on and you start tweaking it, you're going to find that the slightly different setting is going to be much better. And also, like, from scene to scene is going to ask for variances depending on the screen size, because the perceived brightness, because you understand, we're not just regraining image, we're adjusting image graininess, and the graininess is a perceptual effect, not kind of technical effect, right? And Guy, I would totally encourage you to do so. Thank God that we are now living in a time where we are able to control film grain just by turning a dial. Back in the day, it was nowhere as near as simple as that. And take this ability to the max. And if you can, deliver your clients separate versions for cinema and separate for TV.
Oh yeah, I'm totally capable of delivering separate masters, but the problem is that I never get the opportunity to quote unquote sign off on the big screen.
Well, yeah, there is a poor man's kind of scenario for that, which is basically that you go to your local kind of cinema that is always empty during the morning hours, right? They might have like a first, movie showing at 4 or 5 p.m. So you have this time from, let's say, 9, 10 till midday, that nobody's even going to walk in, right? And you make friends with a projectionist. And, now that the Da Vinci is so mobile, it takes maybe a laptop and an SSD and an SDI card that you can just quickly plug in and do it. It doesn't really need to be like a full setup because you just want to do a QC pass and be able to do that. I at the beginning, when I didn't have a projector, I used to make a DCP with different settings. So I would basically cut like a 2 minutes or 4 minutes reel of different scenes, and then I would apply one setting, second setting, and that would take me maybe like a 30, 40 minutes DCP. And I would buy literally the guy a bag of that was the price for, screening that I used to have back in the day in Soho. But Soho was a different and naughty place back then, not like it's now. So, so I'm afraid there is no other way for you to tweak it unless you see it on a projector, because those DLP projectors as well, the DCMA projectors, they have a very particular way how they display and the size of the screen and amplification. You will be surprised how large grain appears on a big screen because it's amplified. There is no workaround. I would love to give you a workaround. The only other workaround is for you to be a little conservative and say, well, I'm not going to go too crazy with this grain if it's going to go on a big screen. If I don't have ability to do a tweak, then just keep it in mind. It's going to get very big and it might look amazing on your LG, but when you blow it up, it might be a little too much. So if you know that you don't have ability to tune it, 10% less, it's a good method.
Okay, thank you.
Yeah, you're welcome. What was the additional grain that came from print stocks, even perceptually significant? I remember copying Kodachrome 64 slides to 4.5 and not seeing perceptual grain. Oh, yeah, but you're talking about the slides. They're different level. In film, we don't have enough. Like we work with a different material. And also think about it. 4x5 slides. They're huge in size. This is also if we were be discussing grain in IMAX movies, right? It's just so good. It's so fine. You think like, oh my God, how can I make that grain, work for me? So yeah, so Thomas, I think what you are doing is considered to be very high end in terms of the grain quality. What about the reversal film stocks? Good question. Maybe Josh, can you maybe, if you're still there, as you walked away, yeah.
Reversal film stocks, really interesting. There's a lot of interesting comments in the chat about for motion picture work, most of the reversal film stocks were cross-processed as negative. Mm-hmm. Therefore, all of the the grain variation by exposure tracks that as negative because it's effectively reversal stocks, or they are effectively a negative stock, and then chemically the dyes come in and get flipped. It's fabulous. But if you are processing it as reversal and want to emulate that grain pattern, then the grain statistics versus exposure level or density would flip. That if you have your larger grain in the darker but the finer grain in the high, is like that experience would in fact flip.
Interesting.
But as I said, most of the motion picture work, and it is mentioned in the chat, where people are quote, oh, I'm shooting reversal, and they think they're shooting reversal, it's getting cross-processed at the lab as negative. So the negative statistical analysis still follows.
Still pops. So they still go negative print. Okay. Very good. Thank you, Josh. Guys, wow, that was a good one. We haven't had such a good session in a while, so I want to thank you all. I'm glad that I can actually go sometimes a little bit beyond just, lift come again. And then we're going to do another one next week where we're going to do just practical stuff. I promise I'm not going to do any slides. And thank you, Josh, for chipping in. Thank you all for dialing in. And also, guys, we're building this community. So, feel free to recommend us to your friends and anybody that who could benefit from these things. This is totally bona fide and, just a way for us to get the right information to the right people And, there's so much noise and so much nonsense out there that I just really want to help you all get to the right information, to the right source, and make the right decisions. Thank you again. And I'm looking forward to seeing you in 1 week time. Take care, everybody. And I see you soon. Bye.